Hello. Sorry about being a little bit slow, guys. My computer just crashed. Okay. Can you guys hear me? All fine? Speakers, microphone array. Perfect. Let's share the screen. Awesome. Okay. Should be working. So I think I might have kicked you guys all out in the Zoom, but that's my computer crashed. So hopefully we're back and running. Okay, I'll give it 3 more minutes. So it's great to see you guys all around. You guys are the last remaining. You guys, but almost done. We have this week and then one more week. And this one's going to be a little bit of a light day for a couple of reasons. I'll get into that in a little bit, but you guys are so close. So you guys are almost certified. Hope you guys have learned a lot throughout this journey, put a lot of effort into setting up, and hope to see it affecting you guys in a positive way. Okay, awesome. So just 2 more minutes, then we'll get going. Okay, we are in to start. Okay, so sorry for the little technical delay. I know you guys are very busy, but it is the weekend. I got some good news for the weekend. This is going to be a little bit of a shorter class today. I know a lot of you people are rebounding from midterms. I got some emails about that. And also, unfortunately, I've had some technical difficulties on the back end. I haven't been able to upload the week 4 video to YouTube. So I know not everybody has had access to viewing that. The video unfortunately corrupted, so I'm going to re-record it. I'm going to do some, hopefully you're going to see if I can recover the files, but if not, I'm going to re-record it and it'll be online very soon. So given that, I'm throttling back a little bit. We're going to take it a little bit easy today. So we're going to be here for about an hour instead of 2. This is part 2 of our lessons on convolution. We're going to be talking about some really interesting topics. We're going to be tackling a new type of problem, and we'll be in and out of here pretty quick. You guys are almost done. So congratulations for you guys. You guys have come so far, and we're almost there. Okay, so thoughts on bacteria. We're going to be covering 3 things today. So I'm going to be talking a lot more about convolutional neural networks. We got into that, kind of the convolutional mindset. We're going to be talking about data, something called data augmentation, which is a lot easier than it sounds. And then we're going to build on top of deep learning. And I'll be talking about that a little bit. On top of that, we have a cool code base we're going to be working with today. I'm going to save you guys the time. I'm just going to show you the code that I wrote. We're going to run through it in our brain, but we're not going to do any retyping because it's rehashing a lot of familiar ideas, and we'll just get you guys out of here a little bit sooner. Okay, so first of all, we have a new problem. And I think you guys should be pretty excited because we're finally moving from, at the very beginning couple of weeks, we were doing problems that were very theoretical, not really real issues. I like to call them textbook issues. Kind of like the questions where it's like, Molly has 82 watermelons and she loses 10. How many watermelons do you have, right? You remember those from elementary school, where you read them and then you think, this is cute. It teaches me about mathematics, but it's not really real world applications. Now we're diving into very real issues. These are algorithms where if you developed, you can put them on your resume and they're pretty cool to have. They have real applications, very real fields, and they're very fleshed out. So let's get into that. The biology department at the University of Guelph runs thousands of experiments every year. It is the job of undergraduate students to identify size and shape of bacteria growth in petri dishes. Now, with schools running more and more experiments, the biology faculty is finding it harder and harder to find students to label the bacteria. They have come to BrainTank deep learning to help them out by labeling this bacteria as best as possible. So we are going to do some bacteria labeling. On the right, we can see 4 different images, and those are all of bacteria. Now, one thing to notice about this bacteria, they can come in very different shapes. Look at this bacteria growth versus these ones. This kind of looks like an outer space scene, kind of funky. 2, these images, they're a little bit off skelter. You see, they're not all the same size. We've dealt with some very pretty data in the past. Our MNES data set, which if you remember is our handwritten digits, they were all the same size. They're all 28 by 28, all black and white. They're all written in the same format. But reality can reflect it very differently. We can have some messier data. So we're going to talk about that a little bit more. Okay. So the data set, awesome. We have 366 images. Each image is a different size. Oh no, that's a problem we should probably talk about. Each image is in color. So these are our first color images, which might sound a little bit more difficult to implement. It's really not. We'll see you. I'll teach you how we treat color images. I'm sure a bunch of you guys must have dealt with color images in the past, even for traditional programming problems. So in this way, if we have 366 images, the traditional 80% split is we put 80% in our training set and the rest of the 20 in our test set. So that is about 366. 300 in our training set and then 66 in our test set. So that's what we'd be doing, but we're not going to do that. We'll see why. All of these images have what is called a bacteria mask, which we will use as the ground truth value. So in the past, the data we worked with was neatly labeled for us. So remember, look back to our handwritten neural network. Remember, we had an image and then a cute little label that said, this is a 5, okay? If you look back to our other stuff, we had doing a regression analysis on diamonds. We had a big list of information, and then we had one little weight for us, okay? We're not dealing with numbers anymore. We're dealing with images. So we're transforming, instead of an image to a label, we're transforming an image to a different type of image, okay? So what we're doing is we're taking these bacteria pictures. Look at this disgusting thing up here. And we're trying to predict a mask around it. So you see this big blob. A student has gone in and drew that circle around the bacteria and said, this is where the bacteria is. So what we're trying to do is pick up on these bacteria growths. There's one there, there's one there, there's one there, there's one there, but not the background stuff, okay? That's the type of challenge we're up to today. Okay, so bolded. Here's our first issue, right? You see that bold change? Okay, made it easy for you guys to pay attention, hopefully. 366 images. That sounds like a lot. One for each day of the year plus an additional one, right? Sounds like a lot. It's not to a model, okay? To put it into perspective, if you remember from our MNIST stuff, we were dealing with tens of thousands of images. 366 is multiple orders of magnitude smaller. And if you know about models, the data set is just as important as the model, and that is going to reflect poorly on our model. So we want to fix this. The other issue, just bolded again. Each image is of a different size. And if you look back to how we did our models in the past, feeding it into neural networks. Awesome, good to see you going in. Sorry. If you look back into the past, if you remember, we came with an output, a vector of, let's say, we would input a deterministic number of pixels. So MNIST, it was a 28 by 28 image. We would feed in 4,096 different images or different pixels into a neural network. And the neural network can only take 4,096 exactly. It can't take less, it can't take more. So if we're dealing with images with varying amounts of pixels, that can be a potential issue. Okay? So how are we going to do that? How are we going to tackle that issue? And one of the main ways we can do that is something called data augmentation. Okay, so data augmentation, here is the definition for you. It's techniques used to increase the amount of data by adding slightly modified copies of the already existing data. Okay, so issue number one, we only have 366 images. We want more. You guys should be familiar with this right here. This is our MNIST data set. That's the handwritten number. And what this data scientist did, I took this from online, is they took that and they did various modifications to it. So you can see they blurred it, they would warp it, they would flip it, they would rotate it, they would add grainy textures to it. They would change in different ways. Sometimes you do not have enough or want more data to train a model. So many deep learning scientists use techniques to morph images into a bunch of slightly different versions. Each of these 20 new images are all still sixes, okay? You can easily identify them as a human. As long as you're not modifying them too much, you should be able to look at these batches of data and say, that is still a 6. Even if it's rotated, even if it's a little bit funky, even if it's blurrier, you can say with confidence that that is a 6. So we can put that into our training data set as a 6. And now instantly from less data, we have 20 times more examples. It makes our model a little bit more robust, okay, to modifications, where instead of having, for example, this pretty little 6 in the middle, our model can now deal with grainier textures. It can deal with flip stuff, maybe something that isn't exactly perpendicular to the page. It's a little bit rotated, skewed. Our model will perform better and we'll have more data to train it on. Okay, these are a few techniques. There's a whole bunch. Okay, we can go through these. Data augmentations, you can just take the original image, you can detexturize it, so that's a type of blurring. You can take the color away from it. You can do the opposite of detexturizing, so edge enhancing, which is essentially, if you've ever gone Photoshop, if you ever play around with scales like that, it's very similar ideas. You can flip, rotate, patch, use only salient edge maps, which is a traditional statistical technique we won't dive too much into. But there's a bunch of different modifications you can do. Another important one for us is you can do different types of cropping, especially in our scene where we have bacteria, and bacteria theoretically should be something, it should be homogeneous. So it's not just one object, it should be a whole bunch of bacteria around. We can cut it into different pieces and train on those different pieces. And I'll show you how we do that. Okay, so the first thing we're gonna do is to make sure all the images are the same size. So that gets rid of our problem where these pixels are a different issue. We will compress them all to a 96 by 96 ratio. Now, an issue you guys might be bringing up to me is now our data is a little bit warped. You can see that this nice circular bacteria is turning a little bit skewed. And that could pose a potential issue. However, if you're not doing this too much, the data and people doing this past says that doesn't actually matter too much. The convolutional neural network will learn that this is warped. If you do it enough, if you do it to all the data, you'll learn that it's the image data going in will come in pre-warped. And it'll actually adjust for that. And so it shouldn't affect the data that much. It actually makes it a little bit more robust. So everything now is 96 by 96 pixels. And what we are going to do is we are going to take our 96 by 96 image and we're going to break it up into little sections like this. So we have one set of bacteria, another set of bacteria. We're going to take from the bottom left, the bottom right, and then right in the middle. And now out of one picture, we have 5. Now what we're going to do to those to increase it to 10 is we're going to take all of those and we're going to flip them. So if you look carefully, bottom left right here, top left right here, it's the exact same image but flipped. So from this, we've taken one image of a bunch of bacteria and produced 10 slightly different ones. It's not a perfect solution. If you took 10 brand new bacteria petri dishes and did image analysis on those and took those and added, you get better results for sure. But unfortunately, we don't have the resources right now. This will iterate upon it. It'll make it a better results, but it's not a perfect solution. Okay. So now our data set, one's changing it. Instead, before we had 366 images, each image is a different size. Now we have 3,660. Awesome. We got a question in the chat. If you're cropping in, wouldn't that affect the count in a picture? Affecting counts in the picture? Yes, it can do that. That's a good question. But the idea is because we're dealing with bacteria, so I'm going to go back. If we're dealing with bacteria like this, we're going to crop only on the training set, okay? Only on the training example. And that'll give more ideas to train on. And then when we test, we'd put in an image that looks a lot more like this, okay? So looking at the intuition behind this is these 10 pictures are slightly modified bacteria images, and they'll teach the model things about shape and texture, okay? So it'll pick out that this blurry stuff in the background is not a part of bacteria, while these nice clean circles are a part of the bacteria. It'll learn how they overlap, how dark spaces correlate with no bacteria, how blue can correlate with bacteria. It'll say that these bacteria are not usually infilled. Usually they have some transparency in the middle. It'll give you contextual ideas about the actual bacteria petri dishes. And so when we go back into our testing, we pass in an image like this, we'll be able to produce our own predicted masks and then use those same rationales, and the model will pick up on the same ideas and will create more of an accurate mask. That's a great question. Okay. So the data set, changing it. Each image is now a, I'm going to say deep learnable size for our scale, 48 by 48, though that's comparable to image sizes we've done in the past. They are going to be larger because now we're working with color. So before we worked with images that were 48 by 48, but they were only in black and white. So they were one channel times 48 times 48. Now we have 3 channels. We have an R channel for red, a blue channel for a B channel for blue, and then a G channel for green. Each of the images are in colors. Masks, however, are in black and white, so they're only one channel. And in fact, they come in only discrete values. The things about masks is that either there's a 1 correlated, like for example, pixels down here will be a 1, and then every other pixel, this purple, will be a 0. So that's what we're trying to procure. Awesome. Moving on. So just a little bit more information. So we have 3,666 images for the input. Each image is 48 by 48. So here are color channels again, 3 times 48 times 48. Each image has a mask coincided with it. So here is what our data looks like once we go in and we break it up. And this is what the mask looks like. Okay. So that is very pretty. For the masks are the same dimensionality. They're 48 by 48. They are black and white. And these are the hand labeled masks that the undergraduate students would typically do. Okay. So for training purposes, we have to remember that we got to crop our images in the same ways. So if this is cropped from the bottom left of an image, we're going to do the exact same with our binary masks. Okay. I also want you to notice that these models are doing a good job at ignoring background radiation. So these little specks in the back are not picked up in the mask. We were only picking up the bacteria that is important. Okay, great. So the model, we're going back to convolution. So here is our list of models we're going to be working with in BrainTank. We were right in the middle. We're doing convolution again. And our model is very similar, very comparable to the one that we did last week. So if you guys were here last week, it's very similar. The main difference is in the input channel. So before we had an input of, remember when I talked about questions, we're going to talk about more. They're actually called filters. It started with one question, and then went to 6, and then 36, and then 100. And here it starts with 3 because we have those 3 color channels. This is where we're going to go into more. And then from the big block of like convolution, the last convolutional layer, convolutional 3, we're going to use a linear layer and transform all the information directly into the image. So we take all the image or all the data from this last convolutional block. We use one neural network layer, and we transform those 3,600 values into 2,404 values. And then remember when we stringed out, we took an image and we stringed it out, we're going to do the opposite. We're going to take those strings and put it back into an image. Okay, we'll show that off a little bit more. More on convolution. Okay, so this is what we talked about last week, just a little bit of a breather because it is a foreign concept to a lot of people. So convolutional neural networks utilize filters to make statements about an image. Each filter asks a different question about the image. Filters get smarter the deeper they are in the network. And in the beginning, you'll look at, is this a horizontal line? And in the end, you'll look at, is this a 7? Okay. I showed you this example where this filter asks, is this a horizontal line, or is there a horizontal line in this square? And you go around the image, and this is called convolution, or it's called striding. But right now, this technique is called a convolution. So it'll stride to the next part of the image. It'll finally get to where there is a horizontal line, and it'll write yes, and it keeps going, it keeps going, it keeps going until it has a full map. Okay, you guys should be familiar with this. It'll ask another question: is there a diagonal line from bottom left to top right? It'll start striding. It'll get to an interesting part of the image where there is a diagonal line. It'll write down yes, or in this case, yes question mark, because there's kind of a diagonal line, but not really the perfect diagonal line. It'll keep striding, and it'll get full data about the image. From there, we stacked it, or we stacked the tables, we put it on top. And then we did another convolution on it. And this time, we're asking higher level questions. So this filter question is there conclusive proof that there is a 7? And we convulsed through it. We showed when we stride to places like the middle, we can see that there is 2 horizontal lines. And then underneath those horizontal lines, our model is saying that there's 2 diagonal lines, which is pretty conclusive that there is a 7 in this image. Okay, so we did that. We took the last convolutional block, and then we strung it out. We got our results. Okay, so I talked to you a little bit about how these questions, which are also called filters, these filters are the parameters of the model. So those are the values that the optimizer is going to change to get our desired results. And it's going to go hand in hand with our loss. So let's see how this works. Okay, so our questions look more like this. Okay, so this is the same application. We have an image window of 7 by 7 pixels. So in this example, since it's in the top left, it's only seeing black pixels. You have a bunch of 0 values. Okay, and now this is where it gets interesting. Here are our question / filter parameters. Our filter parameters look like this. Okay, this is one that is used to detect horizontal lines. Okay, and you'll see why it looks like this. Okay, so what we do is we to generate our result, to generate our answer. So our result is our answer to the question. And our question is there a horizontal line? What actually is happening behind the scenes is you do pixel wide comparisons. So you should be familiar with this. It's just like our y equals mx plus b example. It's just like our neural network examples of the past, except framed a little bit differently. Okay, so you guys should be at least a little bit familiar about what's happening. All we're doing is we're taking our input, so this is our input, and our weight. So each one of these numbers inside the block can be seen as an individual weight, just like in our neural networks, just like in our linear regression. You see, I designed this so it works together, okay? I hope you guys are getting it, clicking in a little bit. You just multiply them together and add up all the results. So input times weight, input times weight. Here we have 0 times 0. If we keep doing that, we'll get down to our weight is now 1, and this is 0. And we'll keep doing that and keep doing that all the way till we get to the end. We'll get 49 different numbers. We add those 49 numbers together and we get 49 because it's 7 by 7 image. We get a result. In this case, since we only had black pixels, everything is 0 over here. Obviously, we get a 0 as our result. We put that into our non-linearity. If you guys don't remember what a non-linearity is, it's a way of compressing high value numbers into a range between 0 and 1. So we get 0.5, a result is 0.5. And you can tell the network that if there's a 0.5, the network will pick up that there's no horizontal line there. If you get 0.5, the model will then in the next layers pick up there's no line there, okay? What we can do next is we can look at when this filter goes up against here. So there is a horizontal line here. You can see it very conclusively. There is a horizontal line now. So our image window has more pixel values, okay? And in this example, I correlated the pixel value of 5 being high and the pixel values of 0 being black, just to make it a little easier to see. So as a result, we keep doing the same thing, 0 times 0, 0 times 0, 0 times 0. Oh, we're getting to the interesting part. We actually have a hit, is we have 1 times 2. If we keep going, we'll get 3 times 5. Keep going, blah, blah, blah. If you add all them up, you get a very high number, okay? So do you see why a map like this, a filter like this, has learned itself to do a good job at picking up on horizontal lines? I hope you do. You can see that it picks up on the horizontal lines. It penalizes lines being up here, or ignores lines at the top and rewards very straight, very true lines right in the middle, okay? So that is a good example. We put that to our result, we put it into our nonlinearity, and you get a result that is almost 1. So that can tell the model that if it's a 1, there's almost 100% a horizontal line there, okay? So that is a little bit behind the scenes, okay? But the interesting thing is that our model isn't just asking one question, it's asking a whole bunch. So here's one, for example, that can pick up on horizontal lines. So the same thing about picking up on vertical lines. This one will pick up on circular shapes. It'll reward circular shapes, okay? The beautiful thing about this is you guys should really like my red numbers, because red numbers mean parameters, and parameters are the numbers you don't have to touch. You don't have to worry about, because the model touches it for you. The model will learn which types of questions it needs to ask to get the best results. We will need to define the numbers of questions asked, and the model will learn that number of filters, okay? So if you're asking a question that has a lot of circles in it, i.e., I don't want to go all the way back, but our bacteria are nice little circles, it'll start learning filters that are cute little circles, because it'll be trying to pick out, is there a bacteria here? And it'll use that image to rebuild that mask, okay? Which I think is quite brilliant. We have different filter hyperparameters. I don't want to go into this that much, because as a deep learning scientist who's worked with convolutional neural networks quite a bit, they seem very arbitrary, very meaningless, and I'll get into it a little bit why after I describe them. So kernel size is the dimension of each filter. So here we can say this is a circular filter of 5 by 5. Here's a circular filter, so it's picking up on circles. You see the shape right here. This one is 7 by 7. Okay, so that's one of the parameters we can change. We can tell the model to make bigger filters, smaller filters. We can ask it about different stride lengths. Okay, so in this example, each time it strides over 1 pixel. So it'll ask that many questions, or it'll ask the same question a certain amount of times, is more accurate. In this case, it's stride of 2. Typically, models use a stride of 1. It's very rare to find something with a stride of 2. There's padding as well, which is adding extra 0 values around an image, helps to maintain constant dimensionality. Okay, these are ideas that are used quite often in convolutional neural networks, and I don't think a convolutional neural network class is complete without at least bringing them up. But we're going to see when we define our models, define our convolutional layers, they ask for these types of values. They ask you, how big do you want the kernels? So do you want them to be asking questions 7 by 7 or 5 by 5? How much stride do you want? But it's very hard to look at a question and say, hey, this type of question, you need a filter size of 10. This one, you need one of 20. This one, you need of 4. In this application, I'm going to stride 3 instead of 1. What typically happens, if you're trying to make a really good convolutional neural network layer, is you kind of just set them however you want, and you trial and error. Okay, so if it's not working with 7, try with 9. If it's not working with 9, try with 10. Stride's not working, maybe you change the stride. Maybe there's be more padding. So I don't think it's an important tool to necessarily understand exactly the details, the intricacies of why these affect results, because it's very hard to see how they affect results, but they do. So trial and error is your best friend in this case. These are called hyperparameters. So they're parameters about parameters, hyperparameters or meta parameters. You'd be the first one to call them meta parameters if you did, but that's kind of how they act. They can be changed, and you can see how they reflect results. Typically, when I am coding with you guys, I will give you the hyperparameters because I know that they work, just to save us some time. So I'll tell you how much striding you should do, how big your filter should be. And then we'll just run it with those. Okay, so this is just another example of a set of different filters. So these are all 9 by 9 filters, and you can see that they're picking up on different shapes. So this ones are picking up on circles. They can also pick up on texture, so like a checkerboard texture. Maybe that's trying to see if it can measure like different grainy qualities. For example, if you're taking a lot of pictures of animals, this could be a good quality to pick up on like fur textures. But there's a bunch of different shapes, and the convolutional network picked them up themselves. No one said, okay, we need to add some horizontal lines, we need to add some vertical lines. The convolutional network did it all by itself, right? This filter is to measure if there's nothing there, which is kind of interesting. Okay, keep going. Okay, loss function. This is where I want to tell you a little bit about the beauty of deep learning in the most holistic way. Okay, so remember, loss functions are just mathematical formulae which give positive model effects when minimized. That's it. It's very general. It's a very general term. You can make a whole bunch of different loss functions, try them out, see how they work for different applications. Okay, so as a result, they can be open-ended and they can be complex or simple. Okay, so in the past, if you remember, we used some pretty popular ones. There was the mean squared error. There's cross entropy loss, which got a little bit more hairy. Mean squared error, very straightforward. They both produce desirable results in different situations. Now we have a completely new type of problem. We're going to need two new different type of loss. So we have absolutely a new type of problem today. Our model produces an image that should look identical to the mask if trained properly. So we're going to try to create a bunch of our little clones of these masks. Okay. As a result, we need a metric to measure similarity between ground truth mass and our predicted mass. To do this, we're going to check out other people's work. Okay, we're going to steal. If you want to be harsh about it, if you want to be kind, it's called building upon the foundations of academia. If you want to be professional, but it's stealing. And that's a brilliant thing about deep learning, is that you build upon other people's work. So I'm going to go into the formula we're going to steal in a little bit. So deep learning is an extremely open field with many people and institutions giving out new models, losses, theories for absolutely free. There's a great website called Papers with Code. which is very user-friendly, very beginner-friendly to some sense. It is an academic website, but for an academic website, it's great for new users. And it's great for sorting out different AI papers and giving you information about it. We're actually going to check it out in a little bit. Okay. So this is what the website typically looks like. It has a bunch of different issues. These are all from universities, or like Google posts a lot, or different academic institutions or journals. And they just have a whole bunch of different papers you can read. I got something called SSIM from this paper, and it's a type of loss function. Okay, so it was developed from University of Waterloo. They gave us actually a very nice Git repository. I can bring that up right now. Let's just take a break from this. I can bring it up. Give me a second. A little interactive here. So from Waterloo, they created a Git repository that they produced a loss function used for image similarity. Okay, so you can see in this nice little GIF right here, they have a picture of Albert Einstein, and they have a picture of a bunch of fluff. And you can see that the measure goes up the more close it gets to Albert Einstein. So it picks up on shape. We're going to steal this. We're actually directly going to download it. They teach you how to use it. They want you to use it. And we're going to use it to as a loss function for our model. Okay, so looking at the example before, this presents. It produces a very small number when you're doing very bad, and a very high number. It maxes out on 1. If you have 2 identical images, it's going to be 1 and 1. If you have 2 completely different images, it's going to be 1 and 0. But it maxes out when the image is almost identical at 1. Okay, this is an issue. If you remember, our one rule of loss functions is we minimize our loss functions. So to reverse that, we're just going to do 1 minus. Okay, so it's very simple. In this case, it would be 1 minus 0.9255, which you get a very low loss. In this case, 1 minus 0.0896 is a very high. So we just flipped it around. So I didn't steal it all. I actually was the one who developed the 1 minus. So building upon academia, that's the whole goal. Okay. So I recommend, if you want to be a great deep learning scientist, if you want to take from being okay deep learning scientist, to check out some of these resources, really expand yourself, maybe read some academic papers. I can give you guys some very great intro academic papers if you're really interested in reading them, but there's a lot of resources out there. So take advantage while you can. Okay. So by the way, the name of this is called SSIM, or structural similarity measure. Okay. Just to show you, before I was talking about how loss functions can be easy or hard, I'm not going to get into the details of SSIM. I have read this paper. It is quite interesting. It's very heavy. It's very statistically driven. There's a lot of formula. It can be quite tough, but I just want to show you how they're using all these complex measures. This is their workflow. They're doing a bunch of math and all this stuff. They're doing a bunch of statistics to see if their measure is correct, right? And we get that for free. So we can just use it. A lot of very smart people use it as a backbone. They have very great results. They have proof around it. So instead of us having to develop something that looks like this, we can do something. We can just take it and use it in our work for different applications. And that is a very, very common. That is actually one of the foundational ideas of academic work in not only deep learning scientists, but in a bunch of different fields. Okay. Okay. So that is our code, or that is our PowerPoint. What I'm going to do now is I wrote out some code for this problem just to make sure it works and to show you guys a little bit. I'm not going to ask you guys to code it because it's a lot of refreshing. The training is also a little bit annoying. I'm just going to step through it, show you what's happening, and then we'll get you guys out of here pretty soon. Also, before we do that, I wanted to show you guys the website a little bit more. I didn't give you that much, but Papers with Code is very interesting. It's very great. Okay. You can go here. So the 3 websites I showed you last week, I showed you the PyTorch website, which is great tutorials about how to code in PyTorch. great website, Kaggle, which give a lot of great data sets. And then this one, the last one I want you guys to remember, if you guys want to remember anything from this class, is papers with code. So some of them can be quite difficult, right? There's a whole different things. There's robotics, there's image stuff. You can look at some of the new papers. So these ones are just coming out. This one came out yesterday. You can look at some of the greatest ones. So here's actually the paper that introduced PyTorch. Pretty cool. There's some really famous paintings here, or not paintings, algorithms here. You can look at, if you go to browse state of the art, if you have a field you're very interested in, so natural language processing is something we're doing next week. And specifically, I'll get into something called sentiment analysis, okay, which is what we're doing next week. So sentiment analysis is taking a sentence and seeing if it has a positive, a negative, or like a neutral response. So for example, a famous example is they take IMDb written reviews. So it'll say this movie is very bad. And we want to use deep learning to figure out if that's a negative sentence, a positive one, or a neutral one. So checking out here, you can go down, you can check out all these data sets. So here's the IMDb movie review data set that I talked about. And you can read all about it. You can download it from this page. And you can also, if you want to learn how to do it, you can go to, these are the papers. If you click here, there's a bunch of different papers that tackle the issue. So here is the best model. This is a 97% accuracy in sentiment analysis. So that will be able to tell you that this is a good movie 97% of the time. They can be quite difficult. If you want to go to the bottom, here we're using a convolutional neural network, so you should be used to that. We can click that, and it'll just give you the PDF, and you can read it. It's absolutely for free. So we have researchers out of New York, and we have a researcher out of in China, I believe, at Baidu, and also at Rutgers. Interesting. And you can read it. Convolutional networks is a neural network that can help you blah, 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 blah. You can check out what it's doing. And give it a go. So this is a great way to learn, okay? So that's a great website. Okay, now it's time for the code. Let's step through it. Sorry if I'm a little bit everywhere. Okay, let's start from the very beginning. So we procure our data set, and I'll show you a little bit what that looks like. So for data in train loader, I'll just print it out for us. I'll make it very easy. Just get the images equals batch. Uh-oh, that's the wrong key there. Images, and then we can show, we also want our masks. So our masks is, if we take from our batch, do our masks. And then we're going to use, I always have a visualization technique for you guys. This one's called display data once again. So we can just display the data, see the images, see the masks, okay? Break it off, and then that's all we need to do. We'll just ignore all the rest. Okay, it's interesting, it's image. Is it batch and data? I don't know why I call it batch. Okay, and it is image. Okay, there we are. Image masks. I mess up my plurals all the time. Okay, so here it is. Here is some of our data, and here are the masks. Okay, you can see that it can get quite complicated. Look at all this background fluff. But this was the only real alive intact bacteria. Sometimes you see right here, there is a bacteria right here that looks like maybe it should have been scored, but this is actually a dead or broken bacteria, but it's not a part of the set. Okay, so that is what our data looks like. Our model, we're just going to step through it again. Just look at the code. I'm going to save you guys time. We're not going to rewrite it all. We have our 3 convolutional layers. Okay, we have 3 in channels to 6 out. So remember, those are our 3 filters that'll look at the image channels. Those are the color channels. That's why there's 3. and then we'll produce 6 out. That is an arbitrary number. It's just a number that works. You can try playing around with increasing that number, decreasing that number, but its number of channels is another one of those hyperparameters, okay? It starts with a kernel size of 7, padding of 3, and we have a bunch of different layers, okay? We did this last time. Out of that, it goes out, we take the last layer, all the information from the last layer, and we put it into a linear net that produces the right size result. So it'll create a 48 by 48 image. We also have our helpers. So if you remember max pool from last time, which helps reduce some of the redundancies inside of the convolutional network. We have our non-linearity, and we have our batch normalization. Okay, so that is the medicine for a convolutional neural network that'll just help it move along. Going through, we bring it through the convolutional network. We reduce the size. We use our activation feature, and then we batch normalize it, and we do that for all of our layers. On the way out, we'll get a big string of data that is 48 by 48 long. So that is 48 by 48 is a big number. Don't remember exactly what it is. We're going to put that into our linear layer, and then we'll create our images. Okay. In our training, we're going to train it for 50 epoch. I've already done this training for you, but it basically is the same exact idea that we've done this entire time. It takes our image, our mask, our model takes our image and produces its own prediction mask. And then we use an SSIM loss that I talked about before to generate our loss. And if you go up to SSIM loss, you can see that I literally just ripped it directly from the people's GitHub page, okay? So SSIM is the function. You add the image and the target, and then here's my little addition to it is a 1 minus. Okay, returns the loss, works perfectly. Add those together. We are not going to train it because I already have it trained for us. Okay, so we have our model state. We're going to load from our model state. And let's see how the results work. Okay, so if we run it, it'll just display a bunch of data. Okay. Great. Okay. Now we can see that the mass in the middle and the mass on the right, it doesn't necessarily do the most brilliant job. Okay, this is a little bit of a trickier situation, but we're trying our best to replicate. This is not. You know what? This is not. Unfortunately, this is my untrained one. I don't know. Oh, I gotta train that a little bit longer. Unfortunately, that is an untrained version of the model state. I think I confused my two versions. That's gonna take a while to train, unfortunately. So what I'm gonna do is on the Instagram, I'll post the correct looking results, what it should look like. Shouldn't be that much of an issue. I'm sorry. When I tested this out, I had the correct model state, I guess, written over of this model state that it was downloaded from the GitHub. So wasn't producing the correct results, but the one that I had before was like bang on. It looked really good. Unfortunately, that's not quite the right results, but I hope you guys get the idea. I hope you guys enjoy your weekend again. This was a little bit of a short one, like I said before. I hope you guys have fun catching up on your data. Yeah, so my previous examples were like, it was very exact. It almost looked exactly the same. I'm sorry for that not being available for you guys. I'll get those images posted on the Instagram just to show you. Yeah, that's a little bit disappointing. But out of this, I hope you guys had a good weekend. For next week, don't think I'm always taking it easy on you. Next week, the last week, is going to be a little bit tiny of a longer class. It is my personal favorite subject. We're diving into something called natural language processing. So we are actually going to tackle that sentiment analysis problem before. That's a really fun one. I think there's some really cool techniques in solving it. It is a lot more, it reminds you a lot more of the human brain, which I always love to see because I think that's such a great and interesting parallel. Sorry for the disappointing results again. We're also going to do more coding next week, so expect that. From there, I have your guys' attendance. I've been writing it down. So if you've attended 4 out of the 6, if you've made it, or if you've sent me an email saying, hey, I'm checking out the online, I'm checking out the YouTube, I can't do the weekend, I'll take your word for it, and you guys will get your certificates coming in the mail. I'll be in contact with you guys very soon. But other than that, I hope you guys enjoyed your weekend. Enjoy the weekend continuing. I mean, I hope you guys, I guess the weekend just started, obviously. Congratulations on being out of midterms. I know that's a big stress. Other than that, we're all done for the day. Okay. I told you I had a short one. So I hope you enjoy your weekend and have a good one. I'll see you guys later. See you guys. There we go.